There are times when we want to estimate the pore pressure not while we're actively drilling, right? We want to sort of get an idea of what it will be. This is very important ahead of the drill bit, right? So again, while we're drilling, it's nice to know what the pressure is out in front of the drill bit, so that we can avoid, or if we're coming up on a tilted sand where you have a centroid effect, if we know that we're entering that, then we can adjust the mud weight to account for that, so that when we go into it, we don't have a problem. Right? And so, you have sonic waves that you can measure out ahead of the drill bit, and you can make some inferences about that. We can also just estimate the pore pressure based on some theory. Okay. So one of those would be a confined compaction experiment. So if we have a core, we can go to the laboratory and we can test it in one of two ways. Typically, what's called a triaxial or hydrostatic compression test. So you have a core, and you isolate the core with an impermeable membrane, and then you stick this in a hydrostatic confining vessel. You stick it in a bath of fluid, basically, and you pressurize the fluid such that you confine this on all sides, and then you mechanically apply a load to the top and bottom, so we compress this guy. Okay? But the hydrostatic component is important, because if it was unconfined, we would just fail it immediately, right? I mean, well, not immediately, but very quickly we would fail it. So in this case, we compress it, and we can either measure or infer the porosity as we do this. Okay? The other type of test is what I think Zoback calls it what does he call it? A sleeved compression test, or sleeved uniaxial compression test. I would call it a one-dimensional strain test. So you actually stick the core into a sleeve that's much, much stronger, typically like steel. You stick it in there so that it doesn't allow any radial expansion whatsoever. And then you apply the force. And you do the same thing. Okay? And when you do that, you'll generate a curve that looks something like this, right? So this is porosity. This case is for shale, the shale. So you have a porosity versus effective vertical stress. So the effective vertical stress here we're actually applying mechanically. Remember what the effective stress is. It is what? The effective vertical stress. So I'll put a little V here. Well, what's the effective stress? We covered it last time, right? The effective stress is the stress minus the pore pressure, right? And so if S is the say we have something like this, depending on the exact scenario. Yeah, it'd probably be like this, actually. So we'd have minus the pore pressure. So what's the effective vertical stress? It's just that, right? So we go to the lab and we do these tests, and it turns out that this curve that, so the tests were performed and measurements were made where the dots are. But you can see that line fits those quite well. And the equation that corresponds to that line is this guy, okay, where I really wish I had the ability to write on the screen. I'm going to try to do this. So this point here where it crosses the origin is phi 0. So that's the porosity at 0 effective vertical stress. And then beta is a fitting parameter that matches, that it gives you the match to this curve. Okay? So once we do these tests in a laboratory, we have phi 0, we have beta, we can estimate the vertical stress from the overburden, right? And then if we can measure the porosity in some way, the only unknown is the pore pressure, and we can solve that equation, right? And so we can actually just write down the solution of that equation, but I'm a computer guy, so I'm going to make a function. I'll call it compaction function. And it's going to take as arguments the pore pressure and phi. And the vertical stress, so I want to solve this. I want to try to estimate what the pore pressure is at a depth of 2 kilometers. Okay? So my depth is 2 kilometers, and the overburden stress increases at what? Do you remember? It's in SI units. It's okay if you don't remember. I actually had to look it up just myself this morning because I didn't remember. It's 23 megapascal per kilometer. So at 2 kilometers, I have a vertical stress 23 times 2. Okay? And then I'm going to write that equation. I'm going to write it on, I had phi equals phi 0 e to the minus beta SV minus PP. I'm going to write it like this: phi minus phi 0 e to the minus beta SV minus equals 0. And the reason I'm going to do that is because I want to solve this numerically, and I'm going to use Newton. Remember from the numerical methods class, Newton's method, right? So I'm going to use Newton's. By the way, you do not need to solve this numerically. I can code it up faster than I could write down the solution. So, and you might imagine a scenario where this equation, this works well for shales. Maybe some other rock, this fit doesn't work very well. And so you might need a more complex expression there. And what the approach I'm about to take would be more general. You could solve, whatever your expression was. So I'm going to have phi minus, and I'm going to plug in some numbers. So from that plot that I just showed you, the numbers for phi 0 is 3.86, and then I'm going to multiply that e to the minus 3.13. So this is the beta number. Beta is minus 3.13 times 10 to the minus 2. Okay. And then I'm going to SV minus PP. Okay. So Anybody, do we have any Python programmers here? Nobody? Okay. It's not that that's not that different than MATLAB actually. But it just, so I defined the function. The function's called compaction function. In MATLAB, I think you just say function, compaction function. So I'm going to use the function fsolve. I think in MATLAB it's called f0. I'm going to solve the compaction function. And then I have to give it an initial guess because I'm going to use Newton's method. My initial guess, I'll just use the hydrostatic pressure. And then the porosity, I'm going to say 0.17. So the function takes as arguments the pore pressure and phi, okay? But I'm actually solving this equation for the pore pressure numerically. And then I gave it a second argument, phi, so that I can change it quickly. So just to be clear about what I'm answering when I do this is, what is the pore pressure at an observed porosity of 0.17? Okay? Not sure what some reason it's not executing. Let's see here. Okay. So that's my answer. So again, at an observed porosity of 0.17, I can estimate the pore pressure according to this equation to be about, let's call it 20. Because my significant digits here are only 2, so I can really only say 20. So it turns out that the hydrostatic pressure, or the difference, the hydrostatic decays at 10 megapascal per kilometer. Times 2 kilometers, 20. So at a porosity of 0.17, I basically have hydrostatic pressure, right? So the reason I wanted to code this up is because I want to be able to get out. I want to be able to quickly change this to say 0.26, then I have an overpressure state. And of course, then the beauty of computers is I can do something quickly like I'm going to create an array of porosities that range from 0.1 to 0.4, and then I'm going to actually now do this root solve. I'm going to solve it for every point in that array. And then I should be able to quickly now get a plot. So this is the pore pressure. Again, this is at 2 kilometers, right? This is the pore pressure over this range of porosity. Okay. What did I tell you hydrostatic was? 20, right? So if I drew a straight line across there, I think I can best I can with my finger. So basically what this says is, that's supposed to be at 20. So at any porosity less than roughly 0.17, then we'll have a hydrostatic or under pressure scenario, and at any porosity greater we'll have an overpressure scenario. Right?